work here, noise is a big factor, but noise is a factor in any kind of measurement. So it's electronic or instrumental measurements in the lab. So what I have to speak about today is generally applicable to anything you'd be doing in the and there we go. Just as a quick review of some of the things that you've already seen here, for the nanopore sensors, our method of making measurements is applying a voltage across, in this case, the dual nanopore sensor, measuring the resulting current. This little amplifier is called a transimpedance amplifier. You may have seen this a little bit in Adam's presentation yesterday. It converts that current into a voltage that can then be read by an analog to digital converter, which converts that voltage into a value on your computer. So you can plot it, so you can do your analysis with it. I'm happy to talk with you about how that works offline. We don't need to go over that now. And here's what our data commonly looks like. In fact, this is pretty darn good data because the event heights, the signal and noise ratio is very good here. The events are pretty big, and you can see the background noise here is not too bad. But this is not always the case by far. So if you don't take anything else from this lecture home with you, just take this one slide with you. When you're doing experiments, you want to know your signal and your noise. And what does that mean? You may not have collected any data yet, but you still need to know, what are my signals going to look like? What do I expect them to look like? And the same thing about the noise. Eventually, when you start making the measurements, you're going to see the noise, and you want to characterize it. And in both of these cases, in both the case 1 and case 2, you want to know the time domain characteristics and the frequency domain characteristics of your noise. And that may be a new concept to you. Time domain is just what we had seen previously here. This plot here, right, is current versus time. So that's time domain. And we'll take a look at what frequency domain really means in a couple of slides. In the event when you're setting up to do your experiments, like I said, you may not know exactly what your signals will look like, but you know what you're expecting. So maybe you need to simulate them in order to look and see what kind of characteristics they're gonna have. And part of this is because the characteristics of your signal and the characteristics of your noise may overlap, and we'll see why that's important. The third part, once you've kind of mapped out this noise and signal issue, you want to identify the types of noises that you're seeing. So when we go back to this time domain noise here, I mean, what can you tell me about that noise there? You look at it and you know, yeah, it's noise. It's not signal, so it must be noise. But I'm saying you need to go into that in more detail. Where is what kind of noise is it? Is it extrinsic? Is it intrinsic? And extrinsic is noises that come in from the environment, or there may be man-made noises. They may be, environmental noises, whatever, that are externally impacting your experiment, or they could be intrinsic to your experiment. And for example, an intrinsic source of noise is a resistor. Any component that conducts electricity and has a resistance to it emits thermal noise. Okay, so the amplifier in our little transimpedance amplifier that I showed you has some intrinsic noise. It's made up of resistors and transistors and diodes, all of which produce a certain amount of noise. So you need to figure out, well, where's the noise coming from? Is it coming from my circuitry? Is it coming from externally? Then on top of that, is it periodic or coherent noise, or is it non-periodic or non-coherent noise? And that's a big difference. So when we say coherent or periodic, it's a voltage in time. It's a voltage change or a current change that repeats itself in time. So a sinusoid, your 120 volt AC sinusoid is periodic, right? And it has a frequency associated with it. The thermal, the noise of resistors and conductive components is thermal noise. That's due to random motion of electrons, and it's temperature related. So the higher the temperature, the more noise, and it's random. It's totally random. It has no periodicity. It has no repeating values, and therefore it's non-coherent, considered non-coherent. So you need to know what are we looking at? What is our noise? And then once you know a little bit about what kind of noise you have, then you can try to identify the source of the noise. And we can apply filters to get rid of noise, and we can also eliminate noise at the source. So we have some some approaches we can take to reduce or eliminate noise. And elimination of the noise source, whatever it may be, and whatever type it may be, is always the most desirable, but not always possible. So let's talk about knowing your signals. So I have a little cartoon here of particles passing through an nanopore, right? So if we have a cubic or a square particle passing through, what's the signal going to look like? Well, it's going to look like a square wave. It's going to have these kind of square corners. This is a cartoon, right? So in reality, there's some issues about rounded corners and things like that. But you get the idea here, right? So we know that's a square wave. If you have a smaller cube going through there, it doesn't occupy the entire pore, so you'll see less of a current change, but it'll have basically the same shape. If that cube is rotated, you're gonna see the edges going through. So you're gonna see something like a triangular waveform. If it's spherical or circular in the 2D like this, you're gonna see something that has circular edges on it. So each one of these, right? So now I know something. I've done a cartoon simulation of my signal. I know maybe which one of these I might expect. And so that gives me some information, and we'll see how we get more information by looking at this. So this is the time domain characteristics of the signal, right? And we're going to talk about how we also, from these pictures, how do we get the frequency domain information from it? So this is how you get to know what do my signals look like. So let's talk quickly about the frequency and time domain. Really, it's a simple concept, but it's confusing maybe when you first see it. But if we have your AM radio dial in your car, if you even have an AM radio in your car anymore, you dial in a station that might be at at 600 kilohertz, at the 6 on the dial here. That represents an AM radio station at 600 kilohertz, and that means that the carrier, or the RF signal that carries the sound that you hear, is a sinusoid at 600 kilohertz, or 600,000 cycles per second, right? If you tune that dial up, if you tune up the dial and you find another station up here at 1200 kilohertz, that station is the signal that station is using to transmit the audio to you is at 1200 kilohertz, and that's those two sinusoids are the time domain signals. But as we said, at 600 kilohertz, if we look at that scale as frequency versus amplitude rather than time versus amplitude, we can tell some interesting things. When we take a sine wave, and this conversion from time to frequency is a Fourier transform. You may have heard of it. Don't get scared of it at this point. We're not going to go through the math, but there are some things we can do visually. There's some transforms we can do without the math that will give us some clues about things that are going on. So both of these sine waves are repetitive, right? So they're periodic. So they're coherent. A sine wave in the time domain results in a single frequency in the frequency domain. So when we do a Fourier transform of this sine wave, 600 kilohertz, it transforms to a spike at 600 kilohertz in the frequency domain. Same thing for the 1200 kilohertz periodic sine wave. Another way to kind of look at that, just conceptually, is here's the plot of a signal in the time domain, and here's its plot in the frequency domain. And this diagram brings me to a comment about how the Fourier transform looks at things. So there's something called the Fourier series. You may have heard of that mathematically. And the Fourier series, or the Fourier theorem, says that I can reproduce any, and I'm going to put the word in here, any weird waveform, as long as it's repetitive. It has to be repetitive in time. But I can reproduce any waveform shape by summing up a series of sine waves of different amplitudes and different frequencies and different phase differences from each other. So as you can see here, we have this kind of funky looking waveform, but it is repetitive. And I can make that waveform by taking 3 sine waves of various amplitudes and phase differences to reproduce that. And by virtue of that, the Fourier transform separates that signal out into the 3 sine waves, and you see those 3 spikes here that represent those. So we can go from a time domain signal over to a frequency domain signal and see what's happening in the frequency domain. We also automatically see that they're periodic, right? So in a Fourier transform, if you do a Fourier transform of a non-periodic or random signal, you just get random stuff back again. So this bottom stuff in this frequency domain plot is the noise, and these are 3 signals here that make up that time domain signal. Okay, why is that important? Well, let's take a look at a couple of these transforms that we can do easily. So let's take some periodic ones. Let's say the time domain signal is that sine wave like we saw before, right? We do a Fourier transform on it, and it has a spike at the frequency, the periodic frequency of the sine wave. Now let's put a sine wave, a really high frequency sine wave, on top of that original sine wave. Well, we still end up with a spike at the lowest frequency, and we end up with a spike at the highest frequency that represents that. We also, if we put a square wave into that, remember I said that we can make any periodic waveform from a sum of sine waves. So that's what this shows. We have a square wave in the time domain. We can make that square wave by a bunch of sine waves at different frequencies and different amplitudes and get that back. If we put a random signal in the time domain, you're just going to get a flat baseline in the frequency domain. Now, for non-periodic things, so let's say you just have one spike, okay? Whoops, sorry. One spike. It takes up, you don't see any individual spikes out here in the frequency domain, but it occupies this amount of area in the frequency domain plot. As the pulse gets wider, you get less low frequency content here. If you have a damp sinusoid, you'll get something that looks kind of Gaussian out here. So this tells us, so our events in a nanopore probably look more like this one, right? So in order for us to pass that in the frequency domain and pass it with fidelity, we have to be able to accommodate all of these frequencies within this little transform area. So that's why it's important to know the time and frequency domain characteristics. And here's some more just common transform pairs, right? So here's an infinitely narrow spike. It produces this flat looking sort of equivalent of random noise response. And again, the rectangular, or here's a Gaussian pulse, and you get a Gaussian back. If you put a triangular pulse in there, like that rotated cube that we showed, you'll get a sine function in the or a sinc function rather in the frequency domain. And if you have that kind of circular or spherical particle, you're going to get something that looks like this out on the frequency domain side. So we don't have to necessarily do it mathematically. We can just kind of guess at things from some of these transform pairs that we have. So why is this again, it was, oh, okay, big deal. Why is this important? So let's say we have a desired signal in the frequency domain. So here's a frequency domain plot. We have a desired signal here, and it's a periodic signal in this case, okay? It's easier to represent here. And let's say we've got one AM radio station nearby that's producing a coherent noise that's getting into our signal. We've got somebody's cell phone up here producing this signal. And then we have the thermal noise, all this grass on the bottom down here, from the resistors in our experiments. So what do we do with this? If we can't get rid of these any other way, we can filter them. But what filter do we apply? How do we know what to do with it? Well, by looking at this, we say we want this desired signal, so let's only pass the area around that desired signal and get rid of everything else. So one way we can do that is by applying a low pass filter that allows everything below this point here to be passed on. And then we can follow that with a high pass filter, okay, which it blocks everything down here to the left at lower frequencies and passes the higher frequencies. And because we've applied them in series, all that we end up passing is the stuff that's in the middle. And these filters can be applied either in hardware or in software. And the result is we get our desired signal, but we still get a little bit of that random noise. We're going to have to live with that. But we've effectively dropped out the really bad signals that we needed, and we've minimized the amount of the incoherent noise down at the bottom. So if we didn't know those frequency domain characteristics, we wouldn't know what frequencies to adjust our filters to. We wouldn't know how to optimize that. We wouldn't know anything. So that's why we have to look at these things and analyze them quantitatively. This slide is just something to show you also that any filters that you apply also affect to some degree your signal, and you have to watch out for those effects. These are RC and RL circuits. Those are the typical hardware filters that we apply. Here we're talking about a low pass filter. You can either implement it with an RC integrator like this or an LR integrator. You have to understand that if you put a square wave in the time domain, you filter it, you'll get something that looks like this out in the time domain. So you have to be cognizant of what's happening in the time domain as well. So once you've filtered in the frequency domain, look back at the time domain and see what's happening. These are the implementations, the hardware implementations for the high pass filter. And you'll see that it actually, what's happening in the low pass filter, you're actually integrating your signal. And in the case of the high pass filter, you're actually differentiating the signal. So you can see that differentiation going on here. So just the things to be aware of. So, so filters are one way to eliminate or reduce noise. There are some other ways that are even better. Like we said, if we can eliminate the noise source in the first place, and here's one of the ways we can do it. So in the case of extrinsic noise, that's generally, in our experiments in electronics work, is in the form of electromagnetic radiation, either that AM radio station electromagnetic radiation from the outlets along the wall or other instruments, whatever. And the important thing to understand about any electromagnetic radiation is Maxwell's laws say that an E field cannot exist without a B field, and these are time varying fields, right? They can't exist without each other in free space. So if a transmitter of an RF signal is going to work, it has to be able to launch that electric and magnetic field. So that means we have two ways that electromagnetic field interferes with our equipment. So it can either capacitively introduce a voltage into our circuitry, or it can magnetically introduce a current into our circuitry. And in the case of the EM source, since it's got both, you're probably going to get both effects. Now, what that tells us also is that one of the ways to eliminate an EM field is by shielding, okay? And that means that, let's say you have an instrument like our transimpedance amplifier and the nanochannel device itself, and we locate that inside of a metallic shield that's grounded, okay? What that's going to do is it's going to shield your instrumentation from the E portion of the electromagnetic field. And it does that by both reflection and attenuation. Depending on the characteristics of that metallic shield, you'll get a certain amount of attenuation and a certain amount of reflection. So the attenuated field, or the attenuated part, is what you really want to rely on. And that when the E field hits the shield, basically it's dissipated in the shield and causes electrons and current to flow to ground. So it shorts out the electron interference and runs it to ground. At certain frequencies, you'll see some reflection, and that's good too, because that's another amount of it that doesn't make it into your circuitry. But the metallic shield is very effective. The problem is it does not do anything to the B field. All right, the B field is magnetic. Putting a shield up isn't going to do much. So the way we deal with with B fields is distance. So whatever the source of this EM field is, the B field falls off as the square of the distance from the source. So that's really important. We do have high mu metal, high permittivity metal shields that we can employ. They're very expensive and they don't work really well. So distance really is your best friend for that. So whatever we can do with the shield is great. If we still have a little bit of E field getting through or a little bit of B field that we couldn't get far enough away from, then that's when we go back and apply those filters that we talked about earlier. But by getting rid of it here, you're going to do a better job with it. One other little piece of that Matt will talk about this a little bit later as well. One other kind of noise is something we call quantization. Well, excuse me. Let's talk about this. Let's talk about aliasing first. So one of the, and this is not a noise. This is not a noise issue. This is a sidebar to any kind of data collection. So, you know, as these days we take all of our measurements and we are taking them with a digital computer in some way, right? So we're using an analog to digital converter or something to take analog voltages, convert that to digital information. The problem is that it's a binary representation of a continuous signal, and you can't really do that. You can only do it as an approximation. So an analog to digital converter actually chops things up into individual. You can see the little jags here on the sinusoid. That's one issue. The other issue is it takes it in samples, right? So it's taking a sample of the voltage in time, right? If you're sampling it once per second, it takes one value of voltage every second. Or in our case, it may be taking a value of voltage 100,000 times a second, but it's still a one point in time. And if you don't take those samples fast enough, you're going to misrepresent the analog signal that you're trying to measure. And that's called aliasing. And an example of that is, let's say we have this sine wave here that has this particular repetition rate. And let's say we're only sampling where those red dots are. Look what happens. It produces, so that's a valid point in a voltage in time. That's another valid point of voltage in time. Same there, same there, same there. And these are evenly spaced. Look what it does. It's going to make you think that you're measuring a sine wave that looks like this rather than the sine wave that it's showing. So it's just misled you. So you must sample at, there's something called the Nyquist theorem. You must sample at least 2 times the frequency of the signal you're trying to reproduce. Now that's only good for a sine wave. If you have a square wave, and remember when we did the Fourier transform of a square wave, we got not only the lowest frequency, but all this high frequency content, the more sine waves at high frequencies. You'll turn a square wave into a sine wave if you don't sample it fast enough, is really what's going on here. And here's an example of that. Here's these transforms again, right? So here we have a sine wave. When we do a Fourier transform on it, we get that, you know, a frequency F1, which is the frequency of that sine wave. If we have that sine wave again with a higher frequency sine wave running on top of it, if we want to reproduce that faithfully, what's the maximum frequency content there is now F2 rather than F1. Nyquist says that if you just have a single sinusoid, you have to sample at least 2 times the frequency of that signal to reproduce it. If this signal is applied, now you have F1, but you also have a sine wave at much higher frequency. So for this one, you've got to do 2 times the highest frequency. Same thing for the square wave. Now you've got both the fundamental repetition frequency here at F1, and you have all of the higher order harmonics that are required to reproduce that square wave. So here you've got to go out to 2 times the highest frequency content of that signal. Now let's take a look at our, we said this kind of pulsatile signal probably represents our events in a nanopore best. So what frequency, what sampling frequency do we have to have in order to pass that reliably? Well, here, look what happens. You've got frequency content all in here, and you've got a little bit here and a little bit here. So you're going to have to come out to this frequency here 2 times that frequency. Again, this is why you need to know your signals, both so you can handle any noise that impinges upon them, and so that you can sample them properly. So that's how we look at it. Now back to these little stair steps like we saw in the sine wave here. When we convert with an analog to digital converter, when we convert that continuously changing analog voltage into a digital voltage, we convert it as stair steps, and the resolution of our voltage conversion is based on those stair steps. Those stair steps are defined by what the bit depth of your analog to digital converter is. So, for example, if we had a 10-bit analog to digital converter, that means there are 2 to the power of 10 or 1024 discrete levels that can be represented. So that translates to a minimum resolution, okay? Now let's say the input range of that 10-bit ADC is 0 to 5 volts. So it can measure any voltage from 0 to 5 volts, but what is its resolution? How accurately can it measure it? That is calculated by taking that full 5-volt range. It's represented by up to 1,024 discrete levels. So that means each of these steps is 0.0049 volts, or gives you a resolution of 4.9 millivolts. So anything below 4.9, you can't measure. You don't know what it is. It's either 0 or 4.9, and that's it. And then every step in between is a multiple of 4.9 millivolts. So the deeper the bit depth, so a 16-bit digital converter would have a much smaller voltage resolution, which would give you a more accurate reading. So you'll also notice that, we converted this, what was nice, smooth sine wave, into this stair-stepped thing. That looks like noise when you start to look at your signals, when you start analyzing your signals. So that quantization error, as seen here, basically just adds to your noise floor. So that's also why it's an important thing to be aware of. So all of that goes back to that first slide. Know your signal and know your noise so that you can handle them properly. We also have some tools, and I brought a little demo tool for you. It's called a noise probe, and you can use that noise probe to help you find extrinsic noise sources. So let me turn that on here so we can see it and see what it's doing. Hello, come on now. Really, you can do that. There we go. All right. I think I have to unmute that. Oh, okay. So I don't want to unmute that. Okay, great. I didn't know if we lost it. So here, what I have is a an analog to digital converter. It's the top trace is the time domain signal. The bottom trace is the Fourier transform of that signal. And what we're using as an input is a little noise probe. Basically, it's a ferrite core with just a simple coil wrapped on it. And we can use this as an antenna, as a pickup to look for noise sources. And you'd be surprised what you might find. So let's take a look. We got a couple of monitors here. Look at that. And look at the characteristics there. So we're a little off scale. Let me back it up on the top side. So you can see some definitely periodic stuff in the top trace. You see some sinusoidal looking stuff. And when you look at the bottom trace, you see all those spikes, right? Each of those spikes is a periodic noise, is a sinusoid, is periodic noise that's being emitted by this LCD screen. You can see the big spike at the left-hand side. That's the fundamental frequency of this noise source. Things that are noise sources are keyboards. Keyboard's not so bad today. Mice. So that's your mouse. There's some noise from your mouse. Power supplies are just terrible. I think I have here's the power supply for the laptop. Say what? Oh, telephone, sometimes you can't. This isn't set up for that high a frequency, but yes, your cell phone is emitting RF signals. These kinds of tools can help you to identify the type of noise and where it's coming from, and also they can help you identify whether your shield is working very well or not. This picks up both the B field and the E field. You can modify this to pick up only the B field. You can shield it with a conductive shield and ground that shield, and it will eliminate just the E field and measure only the B field. And you notice that, right? Did you see that? Why is it doing that? I'm becoming part of the antenna. I have surface area here. The electromagnetic fields that are flowing through this room impinge upon my conductive body, and then I re-radiate it to the probe. So anyway, just some interesting pieces of information, an example of noise sources, where they come from, how you analyze them, and what you do with them. Any questions? So ask me that again in a few months. So that's one of the things, that's a product that I'm in the process of designing. You can build your own. We've held workshops on how to build them, and you have to have an oscilloscope and potentially a preamplifier to go with it. But I'm hoping that that'll become a product. It's not really, you have to roll your own right now, but hopefully soon that'll be the product. In this case, we're using a commercially available oscilloscope box, basically, with the probe. So okay.
Collin, can you hear
Yes.
us? Yeah.
Yes.
I have a question. So you mentioned about electric and magnetic noise, and while electric noise can be eliminated using that metallic shield or the Faraday cage, but you said it's a little hard to eliminate the magnetic field. It's the distance that can help only to eliminate the magnetic field. The question is like, by saying distance, can we use a bigger Faraday cage and kind of put our device right in the middle, not even in the bottom, but then right in the middle, on the Faraday cage to eliminate the noise, or is there any other way to physically reduce the magnetic field?
No, that's correct. Yeah, a larger Faraday cage with the experiment located in the middle or biased toward away from the source can help. Yes. So it's distance any way you can manage it is would be a big help. So you're correct. Yep. And
But the
even
main
go
but the
ahead.
main magnetic and electric source, they also exist within that silver chloride electrode, but those are more coherent noise. And
No, they don't. So the wires that go to your electrodes act as small antennas, and those antennas pick up the noise that's the electromagnetic field, either capacitively or inductively, that they're being bathed in. So the electromagnetic field interacts there. But the noise that we talk about, uh, system noise from the nanopore, that has to do with that's an intrinsic noise source, and that has to do with the resistance or conductivity of the wires and the electrodes themselves, plus the resistance of the nanopore. So if your nanopore is 10 megohms, you can calculate the amount of thermal noise from a 10 megohm resistor, and that'll give you a baseline. Then on top of that, though, you also have ionic noise. So you have because we're applying a voltage and we have moving ions, we also have yet another form of electron motion in this, in the nanopore, and that adds more non-coherent or non-periodic noise. So the thermal noise of the resistance is random or non-periodic, and the ionic noise in the pore is also random and non-periodic.
okay, thank you, Colin.
Sure.